Hey there, Math 126 fans. Night before the final, I can't sleep, so I'm going to answer a couple more questions here late at night. I will not answer questions tomorrow. I have a track meet to go for my youngest son, and then I'm going to go straight to the final. So sort of once I get through this batch, I won't be on the discussion board. Somebody's asking a question about symmetry in center of mass. These are our formulas for center of mass. In a problem like this, we will give the density. One comment, this is just true about double integrals in general. It doesn't even have to do with this. If you want to use symmetry in a double integral, your region has to be symmetric and your density or your function has to be symmetric. Sometimes students get that wrong. We talked about that when we were first doing double integrals, meaning just because you know what the volume is above this, and then later you have a different question that says find the volume above this, you cannot assume that the volume above this is half of the volume above this. The area is half, but it's going to depend on the surface as well. So it would only be half if there was total symmetry above this. For a center of mass density question, sometimes we can quickly test that. So what I mean by that is this. Let's assume you have a region like this that's completely symmetric. It's like an upper half circle. So if the density were constant, like if I told you the density was 5 kilograms per square meter, then you could know right away that x bar is 0. Why do I say that? Well, because if you cut out a little square on either side of here, they're going to have the same density. It's constant. And the region is symmetric. You can't say anything about y bar, so you would still have to compute these two things. That's the idea of symmetry. Now, what if there's actually a formula in here? Well, there are formulas that are symmetric too. For example, if you had x squared plus y squared. So let's take that same region and ask the same question. What happens if you plug in two values on opposite sides? And you can actually do that easily. Just plug in x and minus x and see what happens. Well, if you plug in minus x, are you going to always get the same thing? So that's what I mean by symmetric. You can actually do it without seeing it. Yes, those are the same. It doesn't matter if you plug in, negative 2, 1, positive 2, 1, or negative 2, 1. You're going to get the same thing out of this. So you have to have both things. So even though the y has symmetry in the formula, it does not have symmetry in the region. So you could also say x bar is 0 here. It doesn't save you a ton of time. It basically saves you from computing one integral. So it's not like something you really need to lose sleep over. There are a few other situations. Let me see if I can think of one. If you had a region like this that was symmetric over some other line. I think this is the only other situation I've ever seen where there's symmetry, like there's symmetry this way. To me, it's hard to tell usually if a formula is symmetric this way. Maybe if the density was something to do with x squared plus y squared or distance from the origin, I might be able to figure out that anywhere along here, the density is the same because the densities actually are. In that case, the density on this side is the same as the density on this side, so I would expect x bar and y bar to be the same. Again, that doesn't save us a ton of time, but if you knew that, it saves you like computing one integral. So again, this is not really something to lose any sleep over. If we ask such a question, which we do quite a bit, ask a center of mass question, it's really mostly computation. And the symmetry will save you probably from computing like one integral if there is symmetry. So it's not a huge thing, but if you can clearly see symmetry in the region and in the density, you can use it. That's the point of that. But what's nice about these questions in general is because you have a region, you're going to be able to interpret your final answer and see if it's reasonable. Okay.